Hi, welcome back. In this video, we're going to introduce the definition of a subspace of a vector space and illustrate with a couple of examples. So, if you have a non-empty subset W of a vector space V, then W is called a subspace of V if it's a vector space. In other words, all 10 vector space axioms hold for the subset W with the same addition, vector addition, and the same scalar multiplication that V has. So let's look at an example. Suppose I have the following subset of R3. So W is a set of all ordered triples such that the third component is 0. So the first and second component can be any real number. This is clearly just the xy plane in R3. So let's see if that fits the definition of vector space. And if it does, then this plane is a subspace of R3. First of all, we have to check if it's non-empty. So to check if a set is non-empty, you always have to just present or exhibit a specific element of the set. So I'm just going to write down an ordered triple whose third component is 0. Clearly that's in R3 and it's also in this subset W. So W is non-empty. So the first axiom, the first vector space axiom, is the one that says it has to be closed. The vector space has to be closed under addition. So let's take two ordered triples whose third component is 0. And when we add them together, the first and second components, those are real numbers, and the third component is just 0 plus 0. So we do get something else in W. So that works. It's closed under vector addition. Let's look at the second axiom. That's commutativity of addition. Well, we already know this addition is commutative because the vector space R3, addition is commutative. And the same thing is true for the associativity property of addition of ordered triples. We just got that for free because we're using the same operation. And we're using ordered triples from R3. Axiom 4, we have to make sure we have an identity element. The additive identity element, well, that's the additive identity element from V. It happens to have 0 in the third component, so it's also in W. So we get that for free, which is good. And the fifth axiom, do we have additive inverses? Well, the additive inverse of an ordered triple is just the ordered triple where you multiply each component by -1, and when you multiply 0 by -1, you do get 0. So additive inverses are also in W. The sixth axiom, we want to check that it's closed under scalar multiplication. So we take a vector in W, multiply it by a scalar. Well, in R3, that just means you're multiplying each component by the scalar. And since the last component was 0, anything times 0 is just 0. So we do get something in W. It's closed under scalar multiplication. And the seventh and eighth axioms, those are the two distributive properties. And these we just get for free from the vector space V. We're not changing the addition or scalar multiplication operations at all. So we get a lot of these properties for free. The ninth axiom is another one we get for free because of the associativity property of scalar multiplication. That's not going to change if we just use vectors in a smaller subset. So we got that for free too, because that's just a property of the operation that we are using. We already know that it has these properties. And then the last one, we want to make sure that when we multiply a vector in our subset by the scalar 1, that we get the same vector. And we do, because we're just using scalar multiplication on R3. We're multiplying each component by that scalar. So because we already know it's closed under scalar multiplication, we get this one for free too. So there were really only a couple of things we needed to check here. We needed to check that it was non-empty. We needed to check closure under addition. We needed to check closure under scalar multiplication. And we sort of had to check also that we had an additive inverse and a zero vector, or an additive identity vector. But it turns out all of those things, and everything else came for free from the operations that R3 had. We inherited all those other axioms from R3. So the ones that we did have to check, a lot of them really come for free just from closure under addition and scalar multiplication. So there really are only a couple things we have to check. So that's where the next theorem comes from. Theorem 4.5 is the subspace test. So this says that if W is a non-empty subset of a vector space V, then it turns out W is a subspace of V when the two closure conditions hold. So if U and V are in W, then U plus V has to be in W. And if U is in W and C is any scalar, then C times U has to be in W. It has to be closed under addition and scalar multiplication. So really, there are only three things we have to check. We have to make sure the subset is non-empty. We just have to exhibit something that we know is in that subset. And then we just have to check closure under the addition operation and closure under scalar multiplication. And everything else falls under these three things. So for example, if you want to know if the subset contains additive inverses for every element of the subset, but you already know it's non-empty, you already know it's closed under addition and scalar multiplication, Theorem 4.4, property 4, which you are going to prove in your written assignment, says that the additive inverse of a vector in a vector space always turns out to be the scalar -1 times the vector, right? So you're going to prove that. So we know that's true of all vector spaces. So we know this, if we know we have a subspace, we know it's closed under scalar multiplication. So we get additive inverses for free because we know it's closed under scalar multiplication, so it's got to have additive inverses. So all those other properties either fall under closure, these two closure properties, or we get for free because we get the operations from the bigger vector space. All right, let's look at another example. So a couple of points I want to make are every vector space V automatically has two subspaces. The zero vector, a set that just contains one vector called the zero vector, which really means additive identity vector. It may or may not be a zero, in R2 or R3 or Rn. It could be a zero polynomial, a matrix of all zeros, whatever the additive identity element is in your vector space. If you just take that element, call that a subset, it turns out it will be closed under addition and closed under scalar multiplication. And so that's a subspace. It's not a very interesting one, so we call it the trivial subspace. The other subspace all vector spaces have is just the vector space itself, V. So V is a subset of V, and V is a vector space, so we can call it a subspace. It's a subspace of itself. So those are the two subspaces that every vector space always has. If it has any more subspaces, that is something that has to be checked. All right. For example, the set that just contains the 2 by 3 zero matrix is a subspace the trivial subspace of M23. Also, P5 is a subspace of P5. All right, so those are just two examples of subspaces we always get for free. All right, another example, let's think about the following subset of the set of all continuous functions. All the functions continuous on the entire real line. Let's consider the subset W consisting of all functions in C negative infinity to infinity, so it's a function continuous on the entire real line, such that f of x is non-negative for all x. So all non-negative continuous functions. Is that a subspace of the vector space of all continuous functions? Well, it's non-empty because I can point to one element, the function g of x equals e to the x. That's clearly non-negative for all x, so it's in W. So W is non-empty. So now all we have to do is check closure under addition and closure under scalar multiplication. So if we take two functions that are non-negative, they're continuous everywhere and non-negative, and we want to see if the sum f plus g is also non-negative, we use the usual addition of functions and compute f of x plus g of x. Since those are both non-negative, they're both greater than or equal to 0, when we add them together, we get a function that's non-negative. So the sum, f plus g, is another function that's also in W. What about scalar multiplication? Well, if we take our example g of x equals e to the x, that's clearly non-negative, but we multiply it by the scalar -1, we get negative e to the x. This is not non-negative. This is actually less than 0 for all x. So that's not in W. So it's not closed under scalar multiplication. So this is not a subspace of our vector space of continuous functions. All right, so these are just a couple of quick examples of subspaces, and you'll see more examples and learn more properties of these subspaces, these vector spaces. All right, have fun, and I'll see you in the next video.